Good evening, ladies and gentlemen. Here in Berlin is the afternoon, since the sun is still shining. I would like to introduce Dr. Saleh Khamlichk. He's currently the lecturer and the researcher at the Peninsula University of Technology in South Africa. Dr. Saleh, he holds a doctor title of technology degrees in 2012 from Swan University of Technology, Temba Lab National Research Foundation. I hope I spelled things very good. He focused on the development and design of new materials, zero-dimensional, one-dimensional, two-dimensional nanostructure as well, and nanocomposite for various technological applications, ranging from energy conversion to optic to nanophotonic. He also included in his research the theoretical and computational material science perspective, like molecular dynamic simulation with ab initio quantum mechanical and molecular mechanical method to understand and predict new phenomena at atomic level. So his work is matched very well the work of the group of Professor Ben Youssef and his colleague at the University Mohammed V in Morocco. He designed advanced nanomaterial and thin film based smart solar energy harvesting for the next generation solar energy system, like the concentrated CSP. He produced more than 64 journal publications with high impact factor. And he's also serving as a reviewer for many journals. He's involved in numerous national and international cooperation program in nanotechnology, focusing on promoting the sustainability of renewable energy ecosystem to ensure socio-economic development in Africa. And I think, by the way, he is behind the initiative NESTAF, which he can explain to us about it maybe during his talk. I would like to give him the floor. And the title is already ready on the screen, the nanofluid as advanced heat transfer fluid for the next generation solar thermal energy system. Dr. Saleh, thank you for being a member of the virtual university. Thank you also for accepting to give us and to share with us your knowledge today. And we will be happy to hear your talk. Thank you very much. The floor is yours.
Thank you very much, Professor Nawi. It is actually, I'm very honored to be a member of the Virtual Learning University. So the VLU allowed me really to meet with eminent professors from around the world, not only from Africa or Morocco, but around the world. We are learning from there. I am learning from them. And it helped us, and I wish that this initiative could be extended to other institutions. And I wish that the VLU will attract more scientists and more researchers, so it can contribute to the development of science and technology worldwide, not only in Africa. So this is our wish. So, of course, the title of my presentation today is Nanofluids as Advanced Heat Transfer Fluid for the next generation solar thermal energy systems. As we know that solar thermal energy systems is a technology which was implemented and it is used currently as a renewable source of energy. And from our side, we are trying to contribute to the enhanced performance of this technology by developing what we call new generation or new type of heat transfer fluids, which are called nanofluids in general. So before starting the talk, I would like really to share with you the beauty of Cape Town, the city where I am located at the moment. It's a beautiful city. And as you can see from the map, the African map here, you can really travel by using your car sometimes, but the distance is huge from Morocco to South Africa. So for me, South Africa and Cape Town is like Casablanca, from where I came, from Morocco. So I wish that other Moroccan scientists they could visit us here and see the beauty of this city. It has different places and different touristic places, which are really very beautiful for anyone who wishes to come here and to enjoy with us this beautiful city, Cape Town. So as Professor Nawi mentioned, I am now working with CPUT as a lecturer and researcher. And CPUT actually is an institution which was founded in January 2005. And this institution actually it's a huge institution here in Cape Town, in the Western Cape province, which is here, as you can see from this map here in South Africa. Actually, CPUT has more than 30,000 students and more than 70 programs. But mainly the activities around CPUT are focusing on developing new technologies by using new engineering tools and so on. So I'm really enjoying working with my colleagues at CPUT, and of course, I'm learning from them many technologies when it comes to the engineering aspect of the CSP technologies. So as you can see from this slide, of course, we have a lot of activities going on, and we are insisting mainly on creating collaborations, because we believe through collaborations, things can happen. So for example, as you can see from this figure, I am with my colleagues here visiting what we call Itempa Labs. It is a national research facility here in South Africa. We're working with other researchers there. It helps us to understand materials in general. For example, at Itempa Labs, they have what we call accelerators, where you can accelerate what we call protons in order to study materials in general, particularly materials at the nanoscale. So it is a good place for anyone who is interested in material science in general. So these are my colleagues here, as you can see from the figure. Of course, we have other collaborations with other institutions here in South Africa, like the KwaZulu-Natal universities, like in KwaZulu-Natal and other provinces in South Africa, who are visiting us to see our activities in solar energy in general. These are the researchers from CPUT and from the Energy Institute, of course. I have to really mention that because my colleagues from the Energy Institute at CPUT are really helping us to develop these kind of technologies in general, particularly when it comes to solar thermal energy systems. Of course, as you can see in this figure here, of course, here I am in Germany here at UDE making nanofluids and trying to upscale in order to get some huge quantities in order to test them here in South Africa by using what we call small-scale CSP systems. So now I'm going to start by introducing what we call the solar thermal energy systems, briefly in general. Again, I decided to do this because I wanted to show how nanofluids they can be implemented and how they can be used to enhance the CSP or the solar thermal systems in general. But of course, I believe that there are students with us here who needs to know exactly the technology. So they have to learn about the to see how we can enhance the performance so we can, at the end of the day, have highly performance solar thermal systems by using nanofluids. So before starting, let's look at some history here in general of the CSP. Of course, the CSP technology, it starts a long time ago. Even when I was reading about this technology, I was puzzled to find that Archimedes, he was the first person who invented a reflecting mirror or a parabolic mirror. What he used what we call shields they use in the war. These shields, he coated them with mirrors, and they start to use them to burn what we call bombs. And Khamlichk, he was very clever, and he invented this, and he managed really to win wars by using reflected sun radiation through these parabolic mirrors in general. So around 1878, another scientist from France, his name is Augustin Mochot, he demonstrated a dish with driving steam engine. So the dish will collect the sun radiation and will convert it to heat in order to create steam to drive a steam engine. And this happens at 1878. Of course, at that time, the efficiency was not really very high, but at least scientists and engineers tried their best to come up with new innovation which can help the humanity in order to use this energy coming from the sun in general. In 1913, another scientist from the US, they call him Frank Schumann, is an engineer, inventor, businessman, and so on. He managed to implement the first, or what we call the first plant, using what we call parabolic trough, solar collectors, in the desert, because Egypt, it has huge radiations from the sun. So by using this plant, he managed to create steam in order to drive some kind of pumps for irrigation in the desert. And it worked nicely for him that time. In Italy in 1968, another professor, Giovanni Francia, he managed to implement the first, what we call, plant which produce electricity. It is 1 megawatt plant at that time. Moving forward, in 1982, the US Department of Energy, along with industrial sectors, they began operating Solar One. It's a 10 megawatt central receiver. It's different from the parabolic one. They use the tower, and they use mirrors in order to reflect the sun energy to the top of the tower in order to create heat, and the heat will help in creating steam to drive some turbines and generators to generate electricity at the end of the day. Moving forward, around 2010, almost 34 CSP plants were installed around the world, and they produced around 880 megawatt, which is fantastic. Today, by July 2022, 6.3 gigawatt was produced by using this technology of the solar thermal energy systems. And Spain, other countries in Europe are using it, and the US, as I mentioned. But what makes me happy that other African countries, they start to invest, particularly Morocco. Morocco, I believe now, is the first country in Africa which used the technology in order to produce electricity for the country. And I wish in the future that other African countries would invest in this technology in order to move to renewable energy in general, and to use this technology, which is fantastic, in order to produce electricity in a renewable way. So, and I believe that more enhancement should be done in order to use these kind of technologies in a way that it could help us to move to renewable energy in the future. So, of course, there are different systems when it comes these solar thermal energy systems. There are different configurations, I call it. So, of course, using different configurations, of course, you produce more heat, let's say, if you use a tower. Of course, it's also fantastic
The network with Dr. Saleh, he will be back again. Your mic, Prof, closed. Now back, Dr. Saleh.
Okay.
Okay.
So Dr. Saleh, your mic is closed.
Sorry, Prof. I'm not sure because I think, the issue of the network.
Yes.
So shall I go back for maybe a few slides back, or what I should do exactly?
No, just continue. Just continue.
So it stops here at this slide?
Yeah, you just talk about Morocco and then you continue.
Okay, okay. Okay, sorry for that.
You have to
No
share
problem.
your presentation.
Yes, I'm gonna share it now quickly. Okay.
Okay, that's good.
Okay, yes, I think it's here, I think.
Yeah.
Okay. So I was speaking here at this slide, I think when the internet stopped it, I think. So it was this slide. So anyway, what I mentioned here is the technology of CSP could contribute hugely if we could really enhance the performance of these systems by using a new type of heat transfer fluids in general. And as I mentioned about Morocco and Africa, actually Morocco, they invested hugely in this technology, and it will really contribute in the future in terms of producing energy in a renewable way. So of course, when speaking about solar thermal energy systems, there are different configurations in general, like what we call the linear Fresnel reflectors, where you use mirrors to reflect the sun radiation to a spot or a line, which contain what we call a receiver and also heat transfer fluids in general. But unfortunately, this system is stationary. It doesn't really move with the sun. So comparing that to what we call the parabolic trough solar collector, it's more efficient because for the simple reason, it has the facility of installing what we call a tracking system, which can track the sun during the day and produce more energy from that. Another system, which is the tower, which is used nowadays everywhere in the world. It uses mirrors, of course, and they reflect the sun radiation to a spot which is installed at the top of the tower, which is coated with what we call selective solar absorbers to convert the sun radiation to heat in general and to produce steam for electricity production. There is another system, and of course, it is a stationary, of course, system. And for the parabolic dish, of course, it doesn't use heat transfer fluids. This system here, like the central receiver, the parabolic trough, the linear Fresnel, all of them, they use what we call heat transfer fluids. So this system here, it reflects the sun radiation to a generator or engine, Stirling engine, which is a different mechanism in producing electricity at the end of the day. But they are really very highly efficient at the end of the day. So in my work with my colleagues in South Africa and with other collaborators from Europe, we are trying to make new generation heat transfer fluids, which are nanofluids, in order to enhance the performance of the parabolic systems. So this is our focus at the moment, and we wish in the future, if our nanofluids, if they can show that they could really enhance, and if they can be commercialized in these systems, we will target other systems like the tower, and particularly the tower at the end of the day. So there are other type of solar thermal systems. We call them flat plates or evacuated tubes. Of course, in these systems here, you don't concentrate the sun radiation. So these systems, for example, the flat plate solar heating collector, it has it is coated, by the way. These tubes are coated inside. These are copper tubes are coated with selective absorbent materials, which can absorb the radiation and convert it to heat. And is covered by glass in order to reduce the loss of heat through radiations from the system, so it can be highly efficient. But these systems, they produce heat mainly for domestic use, to heat water for domestic use in general. The evacuated tubes are much better in terms of generating heat because, for the simple reason, they have evacuated tubes. So the evacuated tubes in the system, what they do, they help in reducing the heat loss through radiation. They create vacuum here, and if there are no molecules, so the heat loss through, let's say, through convection is not going to really have a huge impact on this kind of system. So of course, the system, it is efficient, of course, and it is used everywhere for domestic use, even for industrial use in general. So looking at, as I mentioned in previous slide, our interest is mainly focused on using the parabolic trough solar collector in general. So using these kind of systems, of course, we have to understand the mechanisms of heat transfer within the system, and we have to reduce the loss of energy. So by looking at the system here, this is the parabolic mirror, as you can see. So the parabolic mirror, it reflects the sun radiation to the collector, which is a cylinder. So the cylinder is that one, we call it solar receiver. The cylinder, as I mentioned, is coated with selective absorbers to absorb the sun radiation and convert them to heat. That heat should go through the surface of the cylinder to what we call the heat transfer fluid inside the receiver here, the receiver tube. So the issue with this system is when the temperature gets very high, we will have what we call thermal loss through radiation, convection, or conduction. So from the engineering point of view, one should really try to reduce this issue of heat loss through convection, radiation, and conduction. So scientists, what they do, they create vacuum. As I mentioned previously, they have, let's say, a glass cover. They create vacuum to reduce the number of molecules. And if there are no molecules due to the vacuum, of course, the convection, the heat loss through convection is going to be reduced hugely. So the system can be more efficient. Through radiation, what they do, some scientists, they coat the glass with what we call heat mirrors. These are material, these are transparent, but what they do, they try to reflect the radiations coming from the system when it gets hot back to the system. So the radiation, when it goes, it comes back, it is reflected if it is coated with a tin film, which can help in reflecting the radiation back. Through conduction, of course, because these receiver tubes, they are connected to support them within the system. So one should really think about the materials used in building these systems. We have to make sure that we isolate the system if we are using metallic parts in general. So the system could be highly efficient at the end of the day. So as you can see down here, this is a representation of heat transfer modes of a typical parabolic trough collector. And the thermal, this is the thermal resistance model of that system. For example, of course, there is thermal resistance somehow. So one should think about that. For example, if we are looking at the heat transfer fluid, imagine with me now, imagine with me that we are going to use a conventional heat transfer fluid which has less thermal conductivity. which means it will have what we call higher resistance, because the fluid, it has molecules. So the molecules, they must be able to transfer heat within the heat transfer fluid. And if they don't have that capacity, which means we will have resistance within the system of the heat transfer. So when we are speaking about the receiver, of course, one should think about the metals used there, because you don't need your metal to have low thermal conductivity. Otherwise, you will have what we call resistance in terms of transferring the heat. When as I explained, the receiver tube is coated, it absorbs the sun radiation, it's converted to heat. So the heat which was produced should go smoothly to the heat transfer fluid, which means I have to think about the metal. Mainly they use copper or stainless steel, and depends of the thermal conductivity of the metal. And I believe in the future, through material science and engineering, we can even come up with metals which can help us to have highly efficient tubes for these kind of technologies. Again, looking at the annular space here between the receiver and the glass. As I mentioned to you, the support, it can have also, for me, the support should have resistance, because if it has resistance, which means it will not allow the generated energy or heat to go out, that is the idea. But we don't need, as I mentioned, if, for example, if there are molecules here which can help for the heat to be lost through convection, it's not good for us, which means we have to increase what we call the resistance by creating what we call vacuum. So the heat cannot really be lost by convection at the end of the day, and so on. So as I mentioned, there are different parts which should be optimized. In our task here in South Africa, we are trying to enhance the performance of the system by focusing on the heat transfer fluid, because it's, let's say, it's like a core of this system. It's one of the most important part of the CSP. By enhancing the heat transfer fluid, you will enhance the energy transport, this is what we need. By enhancing the energy transport, which means we can create steam in a highly efficient way at the end of the day. So this figure, as you can see with me here, this is a configuration of the receiver tube. As I mentioned to you, for the receiver tube, it has a metallic cylinder. Here it is from steel, is made from steel, and is coated by different materials in order to increase absorption of light coming from the sun. So some scientists, they use what we call different multi-layered configuration, 10 films. They coat the tube with a metallic layer. Again, on the top of the metallic layer, they coat it with a ceramic layer. On the top of the ceramic layer, they coat it with a ceramic layer. Why? So the metallic layer, it helps in reducing the emissivity. It helps in reflecting the far IR and the mid IR, which can cause emissivity. Meaning, if we have high emissivity, it means that the energy which was absorbed from the sun is going to be lost through heat radiation. So if you have a metallic coating like that, it can help in reflecting the heat coming from the sun, from the mid and the far IR, and it can make it more efficient. The ceramic layer is the active material. The ceramic, it means that there is a matrix, let's say like an oxide, and this matrix or this thin film, it has metallic nanoparticles, plasmonic nanoparticles, in order to contribute in terms of enhancing the absorption of light, the sunlight within the system. So the top ceramic layer, sometimes you use like alumina and so on, so it can help in reflecting sometimes if this metallic layer, it reflects some other radiations which is desirable, it can be reflected back by this top ceramic layer. So, which mean this configuration, it's smart, is a multi-layered and smart. Unfortunately, this kind of configuration are still expensive. That's why sometimes evacuated tubes are still having higher cost. But nowadays, there are many companies in China and other countries, they are trying to work hard in order to come up with new configurations to enhance the absorption of light within the system of this tube here. So of course, the nanofluid is going to be there, and it should be highly efficient in order to really make sure that the generated heat is transported in an efficient way. So generally speaking, working with solar thermal systems, of course, there are different parts, as I mentioned, one should look at. The mirrors, which are the concentrators, they should have high reflectance. This should be efficient in terms of reflecting the radiations from the sun toward the receiver. So the reflection should be higher than 90%. Of course, if the mirrors has scratch or if it has dust and so on, the efficiency of the system will go down, which means it will have loss. The receiver, of course, the performance of the receiver should be high. You don't need what we call emissivity, as I mentioned in the previous slide. You should have smart coatings on the top of the cylinder or the receiver tube, which can absorb the sun radiations with less emissivity. That is the only way to reduce what we call losses from what we call the receiver tube. So there are systems, they have direct connection. It means that the generated heat, it will create steam directly in order to produce electricity or heat for industrial heat process. But there are other systems, they use, let's say, what we call energy storage in general. And of course, energy transports, it is done through nanofluids or heat transfer fluids. So the heat transfer fluids, as I mentioned to you, they contribute to higher transport of energy. We must make sure that the used heat transfer fluid, it has high efficiency in terms of thermal transport, or it should have higher thermal conductivity in order to reduce the losses from that. So of course, the energy storage, for a direct connection, it doesn't have energy storage. But if you have this kind of configuration, the energy storage, it's very important for the simple reason, because the sun is not existing during the night. So you would like to have your system operational even during the night. So nowadays, scientists, what they do, they use what we call molten salts. Molten salts, during the day, the heat, let's say the heat transfer fluid, which is used to transport the energy, it can melt them to become, first of all, before going to the melting stage, the molten salts, which are used in this kind of system, they are solid when they are cold. If we heat them up, there are some molten salts based on sodium. If you heat them around, let's say 250, 300, they can change the phase from solid to liquid, which means they will absorb the energy during the day. During the night, we will have the reverse phase transition from liquid to solid, and they will produce heat in order to generate what we call steam to generate electricity and heat in general. So nowadays, most of these technology use energy storage in order to make sure that it's used during the day and during the night. So by looking at this equation here, it shows clearly that the efficiency of a solar thermal system, it has a relation with the optical in terms of concentrators, which mean the concentrator should have high efficiency, as I mentioned, the receiver efficiency, the transport efficiency, the storage efficiency, and the conversion efficiency. So as scientists and engineers, we have to look at all these parameters to come up with highly efficient solar thermal system. In our case, as I mentioned, we are focusing mainly on the transport because we found that this parameter is one of the most important parameters nowadays. Because I believe scientists and engineers, they have done a lot in terms of the optics, the receivers, and also the conversion, but the storage also, it needs a lot of enhancement, of course. So the efficiency of transport is equal to the efficiency of the heat transfer fluid. And that is the reason why we decided to work on nanofluids in order to create highly advanced heat transfer fluids, which are nanofluids. From the literature, as you can see from this table here, borrowed from this paper, which is published sometimes in 2022, it shows clearly that scientists around the world are working hard in order to enhance the efficiency of parabolic trough solar collectors. As you can see with me, they are using nanofluids here in general. For example, I'm not going to read all of these, but I'm just going to take some cases here. For example, there are people who are working on numerical studies, trying to use alumina with oil, titanium oxide with oil, at some, let's say, some 3 volume fraction here. So through numerical analysis, they found an enhancement in the parabolic trough collector of 0.24%, which it seems small, but it's fine. Other scientists, they use aluminum oxide. They use what we call computational fluid dynamics analysis. At 8%, they found 7.6. Jumping quickly to some other scientists who are using experimental studies, like in this case or that case where they use titanium oxide with water, at 2 volume fraction, they found 8.6 enhancement. But the most beautiful one here is, look at with me down there, this Kassasian is a scientist who managed to use what we call multi-wallet carbon nanotubes and also silica in ethylene glycol in a parabolic trough solar collector. They managed to achieve 30.4%. So this is really very good because I believe by using a nanofluid, which is based on that, these scientists, he managed to prove that the enhancement of a parabolic trough, it goes to 30.4%. This means that nanofluids will really contribute to enhance the performance of parabolic trough solar collectors. By enhancing the efficiency of concentrated solar power systems, they could play a key role in decarbonized economy because they can clearly generate electricity without adding any carbon emission. I like this statement because this is the target, because I believe many countries, they are really working hard to decarbonize their economies, particularly in Europe and the advanced countries. By looking at these statistics here, this figure here, so carbon dioxide emission per inhabitant in 2021, actually I borrowed these statistics from this resource here, which was made in 2022, was available by 2022. So if I look at Europe, by the way, this emission is per inhabitant. In Europe, it's around 6.3 tons. South Africa is 7.3. Germany, 8.1. Saudi Arabia is 16.6. That's why Saudi Arabia nowadays, they are investing in this technology hugely, not only in Saudi Arabia, but other countries in the Middle East, because this technology will allow them to decarbonize. Even South Africa, now they are looking at that in order to mitigate and to find new solutions in order to reduce carbon dioxide emission. And I believe even the economy will be affected for those countries who are not looking to shift their technologies to renewable energy and green energy, because even doing in the future business, we have to make sure that our products are coming through a greener way in general. So enhancement of heat transfer using nanofluids. Because by now I believe that I covered aspects in regard to concentrated solar power in general. And now by now we understand that nanofluids, they could really contribute to enhance the performance of concentrated solar power. So let's look at the applications of nanomaterials or nanofluids in solar thermal energy systems. So before looking at that, let's look at the market of heat transfer. Because nowadays they use oils, thermal oils, and the CSP technology. And the market of that is gonna increase hugely. So a study was done, it shows clearly that this market will increase from 3.2 USD billion from 2019 to 8.35 USD billion in 2030. For us, this is a motivation because, as I mentioned, nanofluids will contribute to enhance the performance of these technologies, which means we have to work hard to come up with new generation heat transfer fluids in order to penetrate the market and to find our place in order to commercialize this technology for an enhanced solar thermal systems. What are nanofluids? So this is the question. Simply said, a nanofluid, if we take a conventional heat transfer fluid like a synthetic oil, for example, or ethylene glycol, or even water, if we add nanoparticles to that, we enhance its thermal conductivity, because solids, they have higher thermal conductivity compared to liquids. So the question is, which kind of nanoparticles this should be mixed with what we call the conventional heat transfer fluid. And there are two types of nanofluids. There are nanofluids which has single particle, which means single material. For example, copper or aluminum oxide or copper oxide or so on. And there are what we call hybrid nanofluids. So they call them smart nanofluids because you use different materials with different thermophysical properties in order to enhance the thermal performance and also to enhance the stability at the end of the day. So of course there are here at this talk, I'm speaking about the applications of nanofluids in solar thermal energy systems. But of course there are other applications of nanofluids, not only in solar thermal, but also for automobile applications like for cooling, the engine and so on, electronic cooling, and this is tested at many laboratories, and it shows a promising results in order to cool the electronics using nanofluids. Medical applications. So for the medical applications, we are not speaking about thermophysical. Of course, thermophysical properties is important, but let me give you an example of the use of nanofluids in medicine or medical applications. Plasmonic nanoparticles like gold, they are used to treat some diseases like cancers and so on. So making these kind of plasmonic nanoparticles like gold, silver, to treat diseases, you make nanofluid because you make them in a solvent. That is a nanofluid. So the issue is the technique used to make these nanoparticles. So in medicine, to use a nanofluid, you have to make sure that the nanoparticles are monodispersed, which means they should have the same size, the same properties, because at the nano range, if you have different sizes, which means each and every particle it will have different properties because of the size of the particle. So to use plasmonic nanoparticles in the form of a nanofluid, you have to make sure that the nanoparticles are monodispersed, which means they have narrow size distribution. So they will have the same properties at each and every particle in order to be used in this kind of technology. Detergent for cleaning and so on, it was proven many times. Like silver nanoparticles, you can make it as a nanofluid to clean surfaces. It shows that silver nanoparticles, it kills bacteria. And it was proven in many publications. In military applications, of course, to cool equipment and so on. And also, if I'm speaking about military application, we can speak about nuclear technology, of course. And in the nuclear technology, you need really to have some kind of cooling systems. By using conventional heat transfer fluid, they are not really highly efficient. They are used, yes, I agree, but as scientists, engineers, we have to be able to innovate, to come up with new systems which can help our technologies and to advance our technologies in general. Of course, making nanofluids, there are plenty of materials to use. It's either metallic, like gold, silver, copper, aluminum, iron. Metallic nanoparticles, it's not easy to make, but for gold, silver, of course, because gold, it cannot be oxidized. It's highly stable. But if we are looking at, let's say, copper, aluminum, iron, it's not really easy to make as a metal. Particularly if we are using base fluids like water in general, which has, or other solvents which they have excess of oxygen in general. Sometimes an oxide, it has less thermal conductivity than what we call a metal. So, but there are ways in order to create, let's say, like copper that I'm going to share with you here today by using the laser ablation method in order to make nanofluids. You can use, of course, metal oxides. And of course, there are many scientists around the world. They gave a lot of proofs that metal oxides, they can really contribute in creating highly efficient nanofluids, particularly like aluminum oxide, titanium oxide, and copper oxide in general. Of course, carbon materials based on, let's say, single-walled carbon nanotubes or multi-walled carbon nanotubes, graphite, and so on, this show it also huge contribution in enhancing the thermophysical properties of nanofluids in general. Other nanoparticles like silicon carbide and so on, also they can be used. And the base fluids, of course, when we are speaking about CSP technology, is mineral oil or synthetic oils in general. But for the purpose of doing research, of course, we use mainly water and also ethylene glycol, but we are looking also to use mineral and synthetic oils in the future. So, as you can see from this table here, metallic nanofluids like copper, aluminum, ethylene glycol, at these volume fractions, they show higher thermal enhancement, thermal conductivity enhancement. For the simple reason, because they are metals. Metal oxides, of course, they are contributing, and they show it also enhancement in thermal conductivity in general. So one can select a material to be used and it can really contribute to enhanced performance when it comes to solar thermal energy applications. Making these nanofluids, that is the question, how to make them. So there are different ways. It's either we use a hydrothermal method through chemical reactions. So you can produce nanofluids. You have precursors, you have your solvents, you introduce heat, and you will have some kind of reactions leading to the creations of nanoparticles within the system or within the base fluid, which is used, or the solvent in general. The issue of the hydrothermal method, it's difficult to control what we call the size morphology. For you to be able to control that, you use either surfactants or you use other kind of additives, which they can hinder and they can really reduce the thermophysical properties of the nanofluids at the end of the day. Because these additives, they could be coated on the surface of the nanoparticles or they could be adsorbed on the surface of the nanoparticles, leading to reduced heat transfer and thermal conductivity. But well, researchers are still working on that, and I believe they will come up with highly advanced nanofluids by using this method. And of course, we used this method in our research previously, and we are still looking forward to use it in the future. And currently, we use what we call laser ablation method to make nanofluids. For example, if you have a source of laser like a pulsed Nd:YAG laser, so you can focus the light on a target, and you have your liquid or base fluids, you can ablate your target in order to create the nanoparticles directly in the base fluid without using precursors, without using nothing, just your target and your base fluid. And it's very safe and clean method. It's a really green method. So comparing these two methods, the pulsed laser ablation or laser ablation in liquids and the chemical reduction or the hydrothermal method that I shared with you in the previous slide. As you can see from this figure, it shows clearly that the x-axis, of course, is the nanoparticle mass. This is the mass of the nanoparticle produced through these two techniques. And this is the absolute cost. This is the cost of production of producing these nanoparticles within the base fluid in general. So if I look here carefully to this figure, so the orange line, it shows the chemical reduction if we are using hydrothermal method. At the beginning, when we are working with small amount of nanoparticles, it's good because the cost is low. So now, if I'm working with the laser, it seems like the cost is high, the investment cost. But now, if we are looking to produce these nanoparticles and these nanofluids at higher scales now, so once the mass of the particles gets high, there is a break event. Now the laser showed that the cost it start to go down of the pulsed laser ablation and producing these nanoparticles, which are used in the nanofluid. Sorry, can you hear me, Prof?
Yes. Yeah, of course.
Hello, can you hear me?
Yes. Yeah.
Hello?
Yeah, I hear you.
Can you hear me?
Yes.
Okay, because I believe the network, it's not really strong enough for this.
No,
please just let me know if there is some issues with the network.
it's working. Hello?
Dr. Saleh.
I'm gonna stop my video.
No,
I'm
no,
gonna
you
stop
don't
my
need.
video, so
I think we hear you very good.
can you hear me?
Yes, of course. You maybe you don't hear me, but
Okay.
I hear you.
Okay, because now I took out my video because I think it will also contribute in reducing the quality
No.
of. Yeah.
No, it's perfect. It's perfect.
Okay, thank you. So let's continue from this slide.
Yes.
So as I mentioned, this is a comparison between the two techniques using pulsed laser ablation in liquids and chemical reduction by using hydrothermal technique. So as I mentioned, if you look carefully with me in this figure here, this is the nanoparticle mass and this is the cost, investment cost. So chemical reductions for hydrothermal, it's good if you are targeting small quantities. But if you are looking to scale up the pulsed laser ablation, it becomes much cheaper. So for the simple reason, because as I mentioned in the previous slide, nanoparticles made by hydrothermal methods use additives, which means it's going to be an added cost to clean the nanoparticle surface. So that is where the cost will be going high for the chemical reductions. For the laser ablation, when you are looking at scaling up to producing these nanofluids for the market, it is much better because you produce pure nanoparticles within the nanofluid. So you don't need any extra steps in order to clean and to purify and to do this and that. So this study was done by a group, I think from Germany, who are studying this phenomena. And of course, they have a company and they are commercializing nanofluids for other applications. So this is what they found. They found that the pulsed laser ablation, it's really attractive for anyone who is looking to commercialize and to target the industrial sector in general. So one should go for the pulsed laser ablation in liquids. So another figure, it shows clearly that lasers, the technology of lasers now, it's developed hugely nowadays. So this is the power now nowadays. The power is getting high and the relative price is going down because for the simple reason, there are advancement in lasers. So, and I believe this curve is still going down. Having higher power, which means higher productivity. Higher power, it gives you higher productivity in general, particularly if we are targeting industrial sector in order to commercialize this kind of nanofluids. Really one should look for using pulsed laser ablation in general. So this figure here shows you how one could really scale up production of nanofluids. As I mentioned, we are having a collaboration with some scientists in Germany who managed to innovate a system. They call it continuous flow because again, pulsed laser ablation in liquid. So this is the system that I have been there and I use it extensively. So this system, it's very simple. You have a source of laser. You have mirrors to reflect the beam of light or the pulses of the laser. These are galvanometric mirrors, of course. So why do you use galvanometric mirrors? Because you can turn them in the X and Y axes. So you can play with the laser. You can scan the target. The target, it is installed inside a chamber. This chamber has a glass, quartz glass there, which can allow the pulsed lasers to go straight to the what we call a metallic target, which is inside for the ablation to happen. And you have, of course, your base fluid. In our case, where we use it, what we call ethylene glycol, and you have a pump, and so on. So you can pump your base fluid through the chamber while you are doing ablation, and you can pump it as much as you wish. So you can increase the concentration. You can make letters. Look at this. This is what we made in 2021. It was easy for us to make huge quantities of nanofluids by using this system. Previously, when we used hydrothermal methods, we couldn't achieve this at all. And these nanofluids are still with me, working with them now to study the stability, and I found that they are very, very stable with time. Since 2021, now we are in 2023, and I'm still testing them, and they are still highly stable. For the simple reason, because this system, it can allow you to create very narrow nanoparticles at the nano range, less than 10 nanometers, which they can be stabilized to through what we call electrostatic stabilization in general. So the particles, they can stay within the liquid. They can stay highly dispersed within the liquid. So let me just make this video to show you. I'm not sure if it's going to start. So this is the method. So this is the chamber. So the mirrors are installed inside this system there. The pump is that one. This is the bottle there that you are looking at. The nanofluids, they are pumped. And the beam of lasers. So they are reflected. You see, the beams of lasers come into the system to be reflected inside. And the chamber there. And you are making your nanofluid. There is no waste, no contamination, there is no chemicals, no precursors. So very clean, very nice. You produce your nanofluid and you apply it and you test it nicely and you produce highly stable nanofluids. So the mechanisms, how it works from the physics point of view. The laser, as you can see with me in the previous slide, it interacts with the target. So the laser, it's coming. We have, in our case, we use it copper target. So once the laser interacted with the target, it creates plasma because this laser, it's highly energetic. It causes the surface of the metal to melt and to create a plasma and to be evaporated also. It melts the surface, and because these pulses are very fast, the melted metal, other pulse, it makes it to evaporate and to create plasma, a state of matter where there are only ions and atoms. Highly energetic. This plasma will grow with time, and this process, it happened at the picosecond regime, very fast. So the plasma will grow, and because it's very hot, this plasma, because it's very hot, the surrounded liquid around the plasma will be evaporated, which means you will have a vapor here of what we call the molecules of the liquid, which is ethylene glycol in this case. There are a lot of physics around here, thermodynamics and so on. So the plasma, after some times, and this, it happens at the nanosecond regime, it starts to shrink with time in a fast way. And this cavitation bubble, it starts to grow. It grows, it grows, it grows. And while this plasma is shrinking, because it contains the atoms of the copper, these atoms, they will attract themselves, each other, to create nucleus, and this nucleus will create nanoparticles inside the cavitation bubble. So once the cavitation bubble collapses, the nanoparticles created inside, they will be dispersed inside the liquid. Very simple process, but it's an elegant process. And it's a very clean process and every day. So as I mentioned to you, the pulses of the laser are very short. In our case, we use it nanosecond and picosecond lasers. In South Africa, we use it nanoseconds. In Germany, we use it picosecond lasers. So these pulses are very fast, highly energetic. Once they interact with the surface of the metal, they can melt it. The energy will be absorbed, of course, by the metal, which it will lead to the melting of the metal. Other pulses come in, they cause that melted metals to create what we call a plasma, and you will have what we call shock waves happening around, and the process is just very fast. So for short laser pulses in the nanosecond range, the ablation process is dominated by heat conduction. That's why the atoms or the surface is melted, and evaporation, of course. So these are some results coming from the nanofluids that I showed you here. This is morphology, of course. These are nanoparticles. Here we use it what we call high resolution transmission electron microscope. Of course, we use it different lasers. We use the laser operating at 515 nanometer wavelength, and we use another laser, of course, also at the picosecond regime, but it has a different wavelength. Here, we wanted to find out the impact of the wavelength on the production of the nanoparticles. What we found, by using 515 nanometer laser in terms of wavelength, we managed to produce smaller nanoparticles at the range of 2.5 nanometer. This is a particle size distribution here. This is the statistics coming from these particles. We measured the size of each and every particles, and we came up with this histogram. And it gives us that the average size is around 2.5 with an error factor of 0.31 nanometer. Using a laser of 1064 nanometer, we found that the produced nanoparticles are a little bigger at the range of, let's say, 4.8 nanometer with an error factor of 0.15 nanometer. One could really ask a question, why? Why using different wavelengths give us different sizes? As we know, copper nanoparticles, of course, is a plasmonic, is a metallic nanoparticles. It has what we call plasma resonance at the surface plasma resonance. It means that the phonon at the surface of the metallic nanoparticle, they absorb light. As you can see from the UVVs here of these materials produced, this is copper and ethylene glycol, of course. So the ones which are produced at 515 nanometer, it shows this trend here, or this curve. The one at 1064, they show this, and this is the surface plasma resonance band of the copper here. It shows clearly that we produced copper. But this one, it looks small, it's the intensity of the absorbance. This one, it's high. This one, it shows us that, of course, these wavelengths, it gives us less quantity of the nanoparticles compared to the other one, because the intensity of the absorbance, it's high a little bit there. For the simple reason, as you can see, the surface plasma resonance band, it's around 576 for this guy, and around 500 It means that the absorption, but it's not the wavelength using. What it means, the produced nanoparticles, they will interact with the laser pulses and they will absorb them. And if they absorb them, they will reduce the efficiency of the ablation. And they will cause what we call fragmentation of the nanoparticle. That's why the particles are small, because the copper doesn't absorb this wavelength. It absorbs this wavelength. Once it absorbs that wavelength, the particles, they will have fragmentation, which means they will be divided. They will become very small. But by absorbing the radiation, they cause lower ablation rate. But it's fine, because as you will see with me during the talk today, that you will see that even if we have this phenomenon, but it was good for us. This is what I'm going to prove to you today. Why? So this is the impact of the wavelength. So by looking at the elements there to make sure that we have copper. So this is what we call the energy dispersive X-ray. It is patterns. This shows clearly that we have copper there, copper. The carbon is coming from the grid, use it because it's coated with carbon, and little oxygen there. And this, it doesn't mean that we have an oxide there. It could be a small layer of the oxide, which we couldn't detect. Maybe we have to look for other techniques in order to make sure that the surface, it's not oxidized. But even though the oxygen, it's really very narrow, the peak of the oxygen there. So this, it proves that we managed to produce nanoparticles to create what we call ethylene glycol nanofluid. Now, making these nanofluid, we have really to test it to find out if the nanoparticles, the copper nanoparticles, they contributed to enhance the thermal conductivity of the ethylene glycol. Because ethylene glycol, it's a heat transfer fluid, of course. So we designed this system. This system, they call it guarded hot plate, is a modified one, a cylindrical one. So it has what we call this cylinder, we call it a hot plate or a hot cylinder, which is the inner cylinder. And it has what we call the other cylinder there, which is the cold one. This is the hot and the cold one. So through the Fourier's law, here it's very simple, as you can see. If you apply power to the inner cylinder, you create heat on the surface of this cylinder, which can lead to heat flux through the nanofluid, which is at the inner here, at the annular space. So once we hit the surface of this cylinder, the heat will go through the nanofluid to the cold cylinder. And by using this equation, which shows here the area of the cylinder inside, it shows the distance between the cylinders, and it shows the difference in temperature between the hot and cold cylinder. You can extract what we call thermal conductivity. It is there. Very simple, but it's a very robust method in order to find the thermal conductivity of nanofluids and liquids in general. So this is what we use to prove that our nanofluids, after adding different type of nanoparticles, we can study their thermal performance in terms of thermal conductivity. Because thermal conductivity is very important parameter in this technology. Very simply said, we start with ethylene glycol, pure ethylene glycol. We pump it through the chamber. We make the ablation. We create the nanoparticles. We have our nanofluid, we test it. And we use it, as I mentioned, different wavelengths. And this is what we found. This is the temperature. This is the thermal conductivity. For a sample which made by 1064, it has nanoparticles with diameter of 4.8. It gives us an enhancement of 18% at 380 Kelvin temperature. The other nanoparticles made by 515 nanometer laser, it shows 30% enhancement. At the beginning, I was not happy with my colleagues because of the issue of this fragmentation, and the nanoparticles are absorbing the laser at 515. We were not happy, but after doing the analysis, we found that those nanofluids are the better ones. So sometimes you think that you are not doing something very good, but at the end of the day, it gives the better results. And this is what we found, 30% enhancement. So what is the beauty of this? That our nanofluid, we made them at very low volume fraction of 0.002% for the first time. Because in the literature, there is no report showing a nanofluid with this concentration having this enhancement. So now we are saving materials by using only small amount of the nanoparticles and having higher enhancement. So now what we will do with that nanofluid, we are trying to test it now by using a small scale parabolic trough collector. So we are trying to test these nanofluids for steam production, water desalination, milk pasteurization, and food processing. So these are our intentions, and we would like to test them and to find out how this nanofluid will contribute to these kind of technologies. So as I mentioned, that of course, looking at the volume concentration or the volume fraction is very important, because our Mother Earth, it has limited resources. If we are trying to make nanofluids, which means we are trying to ablate and to use metals and other materials. So we are trying to find out the lowest concentration, which can give us enhancement in terms of thermophysical properties or thermal conductivity of the nanofluid, because this is very important. So by looking at these figures, at different concentrations or volume fractions, here is 0, which means is pure ethylene glycol. By increasing the volume fraction to 0.002, the thermal conductivity is going up. So we didn't want to work above that because we have done that previously. And it's not our interest. Our interest is to come up with nanofluids with the lowest possible volume fraction. As I mentioned, our Mother Earth, it has limited resources, and we have to make sure to use our resources wisely. So in order to use them for different applications and to come up with new technologies and so on. So by changing the volume fractions, it shows clearly that at 0.002, as I showed you, is 30%. 0.0016 is around 19. Even if going down to 0.0004, it's around 5% enhancement, while it's fine at this range. So, but by showing this, we shows clearly that using highly stable nanoparticles made with the techniques which allow you to have very narrow nanoparticles and electrostatically stable, they could really lead to what we call higher efficiencies at the end of the day. So now I shared with you some experimental investigation. So now I'm gonna move to show you what we do in terms of theoretical computational analysis to understand and to predict the thermophysical properties of these nanofluid systems. So I'm going to start by introducing molecular dynamic simulations because I'm using it to study nanofluids and to understand nanofluids and to design new nanofluids. Molecular dynamic simulations, it allows you to create what we call a virtual laboratory in your computer, which can allow you to understand and to tune and to play with different materials to find the best material which can allow you to have high efficiency. Molecular dynamic simulations is a classical, it's based on classical mechanics. It uses Newton's law, of course. The force, this is the force acceleration. All of us, we know that. And by looking at this figure here, if we are looking carefully, the quantum chemistry, it's used to study materials in general. Even at the angstrom regime, you can study atoms, you can study molecules even by using quantum-based calculations. Molecular dynamic, it works, of course, at the nanometer range and also at the nanosecond range. So you can study molecules in general. So quantum simulations, it allows you to include electrons and so on. The issue of quantum calculations is difficult to work with bigger systems. You need huge computational power if you want to use it to study nanofluids, which nowadays, it is almost impossible to use quantum calculations to study a huge number of atoms. It's not, I said impossible, but it will be possible in the future, I believe. But nowadays, we are still limited. So molecular dynamics, it allows you to study these systems, nanofluids with plenty of, let's say, atoms and molecules in general. By going up, Monte Carlo, mesoscale, but these cannot really help you to study these kind of systems at the atomic level and the molecular level, because it will allow you to study systems at the micrometer level. And of course, in the engineering aspect, studying heat transfer, you can apply them. They can give you information for the engineering design and so on. But understanding the system at the atomic molecular level, it's not really, it's not going to help really. For us to be able to understand, we decided to go for molecular dynamic. And sometimes even we combine it with quantum calculations like IPNHUs, because even in the molecular dynamic calculation, you need potentials. Molecular dynamic, as I mentioned, doesn't really include electrons. So you cannot really calculate potentials of interactions and so on between molecules, atoms, and so on using. So sometimes we use IPNHU to calculate and to come up with potentials and to use them for the molecular dynamic at the end of the day. So as I mentioned to you, of course, using quantum calculations is the best. It can give even more accurate results. But the issue we are facing nowadays is the computational power. Because nanofluids, you are dealing with bigger systems. So from here, you can see quantum mechanics. It allows you to study small molecules, crystals, electron dynamics, and so on. And we can, in our case, we use IPNHU to come up with potentials. Sometimes we work even with other scientists to help us to find new potentials and so on to be used in our calculations. Molecular mechanics, of course, you can study polymers, nanomaterials, bigger systems, bulk materials, protein, and so on. And as I mentioned, the Monte Carlo continuum mechanics and so on, finite elements is used in engineering to study macroscopic systems. Of course, I work with my colleagues together. We combine our efforts. So we study things at the nanoscale, of course, at the macroscopic scale, so we can understand even, and that I believe can allow us to come up with new innovations in the future in this regard, by combining different methods and different techniques to understand and to tune the properties and to find out newer properties in order to come up with new technology or new nanofluids at the end of the day, which can help us to enhance the performance of our solar thermal systems. Speaking about molecular dynamic, of course, you create what we call molecules. You create them. I'm going to share with you in the next slide how we do that. You create molecules with initial positions and configuration, and we call it starting configuration. And we assign velocities and positions, initial position, to those molecules and atoms within the system in general. So the force on each atom due to the other atom and its neighbor is calculated. The forces of interaction are also calculated from a knowledge of forces and position and velocities, of course. So the set of atoms and their displacement, it can be fluid. And this is what we are looking for, because remember, dealing with nanofluid is a form of molecules. Nanoparticles, of course, they are solids, and of course, they are a form of atoms. All these molecules and atoms, they have vibrations. They move around, even at room temperature. Now, if you introduce the heat, you increase the vibrations. And this molecule, they start to move around, to vibrate fast, in a fast way. In a fast way, in order, and they will interact between each other and with by doing molecular dynamics, we are trying to follow up and to find these positions with time, so we can understand the behavior of these molecules, because they are the cause of the heat transfer and every day. By performing, to perform this molecular dynamic, and the first step, as I mentioned, you have to define the initial positions of each and every atom within the system or molecule within the system, even their velocities at time 0. And you have to set also the time step in order to follow, because these molecules, sometimes they are moving at the femtosecond regime or so on. So you have to find the right time step for these molecules. You can follow them in a way which can allow you to understand them. Because just imagine if you have lower time step, then the movement of these, or the velocity of the movement of these molecules. So you cannot really follow them. So the question is, at the first step, it's very important. One should really define that, the time step, the position, and so on. The second step, we use what we call Verlet algorithm. And that Verlet algorithm, it helps us to locate these kind of movements accurately and their velocities in general. So the step 3, through the algorithm, it allows us to calculate what we call the forces and energies between these molecules within the system. The step 4, again, after atom movements, location, it will again update. If the molecule it's moved from a position to another position, it will interact with other set of molecules and so on. So you have to register that. At the step number 5, we apply what we call boundary conditions. Temperature and pressure, we have to be controlled, of course, to create a system which can simulate what we call a real laboratory in general. So which means you have to control different parameters from the thermodynamical point of view. So all these steps it should be followed, and a program is created in order to be applied on the system which is created to be studied. So the interaction between these molecules and these particles, let's say the molecules of the solvent and the metallic particles, we have to have potentials, as I mentioned before. So, but in terms of the base fluid, let's say in our case, we use ethylene glycol, but I'm just giving you a general picture here. For example, for the liquid, we use what we call Lennard-Jones potential. And we use, this is the Lennard-Jones potential, by the way. We combine it with what we call electrostatic interactions, because remember, these molecules, they will have their atoms, they will have some kind of electrostatic interactions, of course. What we add to the general potential for the liquid, we add what we call the bond length potential, the bond angle potential, and the torsional potential, or the dihedral. So all of this stuff, they allow you to create a system to simulate the real base fluid, which is used to create the nanofluid within the system. So this is just an example to show you clearly within the system. For example, the bond length potential, it shows you clearly how this molecule is stretching, that bond is stretching there. We're trying to simulate the real molecule here. It's not easy because a real molecule is not like this, of course. Of course, it's not like, we are just trying to model here. But in reality, the molecule, if we cannot really observe it in this way, but this it allows us just to model and to do our calculations. We are trying to model a molecule in a way which we can understand, because from the quantum mechanical point of view, atoms, they have nucleus, electrons, the bonds, they are not like that, they are energies and so on. But they behave like this. You have stretching bonds, like from this potential, you have an angle like that, you have rotational or dihedral like that, torsional. So you have to make sure all these parameters are true to simulate and to model your system. So what we do sometimes, we do calculations or we borrow these kind of informations like the angles and so on from other publications and so on, and we include them in our algorithm in order to do these kind of calculations and to find and to tune and to really simulate the molecules, use it in our nanofluid. So in our nanofluid, of course, as I mentioned to you, it is ethylene glycol. That's the reason I mentioned that using quantum calculations is too difficult at the moment, because look with me how many atoms there and molecules, plenty. Just imagine if you would like to use quantum calculations to come up with and to understand this system. I believe there are scientists with us today who understand that very well. Quantum calculations are very powerful tools, but with this kind of systems, for the moment, it's not really easy. So for our system, as I mentioned, we use what we call this Lennard-Jones potential, which shows clearly the finite distance here. What we call is the finite distance at which the pairwise potential is zero between the two particles within the molecule of the liquid. So this is the depth of the potential of the interaction. And of course, this is the distance or the distance between atoms in general. For the metallic nanoparticles, we use a different kind of potential, because I showed you here previously, what I showed you here, it's all about, this is used to study what we call the liquid itself. But for the metallic nanoparticles, we use what we call embedded atomic model potential. This is the energy. It has an embedded function, of course, that represents the energy required to place an atom E of type alpha into the electron cloud. So this potential, actually, I was working with other scientists who developed this potential, and I'm using it in my calculations, of course. This is the contribution of electrons, and this potential was calculated through IP initio calculations, of course. So the electrons, of course, they are included because this is a metal. Metals actually, they have higher number of electrons. That's why you have to include what we call the electron cloud in general. So to make sure, I'm going to be very fast because the time is running. So to make sure our system, it has a solid nanoparticles and the liquid, so we have done what we call radial distribution function. It shows clearly that the metallic nanoparticle, it has a regular periodic structure, which proves that is a solid. For the liquid, we have this kind of configuration, which prove exactly that the liquid, that the base fluid is liquid. Because as I mentioned, we have to simulate like a virtual lab. We have to make like a virtual laboratory in order to understand this system. So after doing all of that, we have now to extract the thermal conductivity. So we applied what we call Green-Kibo equilibrium molecular dynamic. This equation was applied within the algorithm in order to extract the thermal conductivity from the system. As I mentioned to you, this is a heat flux autocorrelation function. Of course, the molecules are vibrating and they will be stable after some time. They will reach what we call stability. So after the approach 0, we do our integration and we extract what we call the thermal conductivity. And this is the heat flux, which gives us what we call heat flux autocorrelation function. And that is the equation of the heat flux, which has what we call the kinetic, potential energy, the force, and so on. So this kind of calculation, they allow you to extract thermal conductivity and to compare it with what we call experimental results. So this is the experimental result of copper ethylene glycol nanofluid. This is the molecular dynamic again, and this is another one there, which shows you clearly that the molecular dynamic, it allowed us really to come up with results which are comparable with the experimental stuff. This means that it's confirmed that that molecular dynamic approach is a suitable approach in order to design nanofluids. It can be used to design new type of nanofluids every day. So I'm not going to take long because of the time. So we use other kind of calculations. Here, it's what I'm showing you here is a U and Chua theoretical model. It's these scientists, they use what we call Maxwell model. They modify it by using some kind of calculations based on what we call a layered structure around the nanoparticles. They stated that these molecules, they are adsorbed or they approach the particles and they create a layered structure. They call it a layered structure, which can contribute to enhance thermal conductivity through this equation. So this is the nanolayer of the molecule, and that is the equation of that nanolayer. So this equation, it is used to calculate the thermal conductivity at the end of the day to find out if this nanolayer, if it's going to contribute or not. So by doing these kind of calculations, we got more insight to the impact of the nanolayer on the thermophysical properties or thermal conductivity of our nanofluid. So these results are coming from that model of Yuan Chua. So it shows clearly that by increasing the concentration and also increasing the thickness of the layer, we found that if the thickness of the layer is 0, there is no enhancement. By increasing the layer thickness around the nanoparticles, the layer thickness, when I'm speaking about the layer, I'm speaking about the adsorbed molecules of the ethylene glycol around the copper nanoparticles. So this it shows clearly that the nano layer around the particles, it contributes hugely to enhance the thermal conductivity, particularly if the nanoparticle is very small, because this model, it works only if the nanoparticle is less than 10 nanometer. So here, by changing the radius or the size of the nanoparticles, it shows clearly that at higher size, even at higher concentrations, the thermal conductivity, it goes down. This, it means that you need tiny, small nanoparticles at the below 10 nanometer, which it can really have high surface energy due to the surface to volume ratio, of course, because it's a nanoparticles, which can allow attraction of molecules to create this nanolayer, which can contribute to enhance the thermal conductivity. So now these are the experimental results from our nanofluid, and this is the model that I showed you. It shows clearly. So here, this material, this one, it was made by the 515, as I mentioned to you, nanometer wavelength. It shows higher thermal conductivity and also enhanced heat transfer around 30%. The other one, which we use it 1064, it gives us, of course, model, it fits very well the experimental, but again, when using 1064 nanometer, we have only 18% enhancement, which means by using a wavelength of 515, it gives smaller nanoparticles, higher enhancement. So in this study, compared with other studies, so we found an enhancement. This is enhancement, this is a ratio enhancement, concentration, normalize the thermal conductivity, enhancement, which means the enhancement, which is 30% divided by the concentration, we have 15,000. This study. Compared to other studies, they use it higher volume fractions. So these are their enhancement. These studies, they use it mainly copper because we're interested in copper in this study. So in our study, we found that the Picosgreen laser, it gives higher enhancement at very low concentration. So thanks very much to my colleagues at Cape Peninsula University of Technology who contributed hugely and assisted hugely in these kind of studies. Of course, thanks to my colleagues at the African Material Society. These are students from different countries, Sudan, Mozambique, Africa, Uganda, Ethiopia, Ghana. They have been working with me. I enjoyed with them hugely working on this project. We're trying to use this nanofluid with a concentrated solar power to the pasteurization of milk in general and rural area. So the future, we are looking at the future now. So we would like really to implement these kind of technologies in Africa more and to test these nanofluids so we can be advanced and we can contribute to this technology. Thank you very much. And sorry for taking very long. Thank you very much, colleagues.
Thank you very much, Dr. Saleh Khamlichk. This is an excellent talk, and you have made the talk very clear, and all issue from the experimental point of view and from theoretical point of view, everything was excellent. Thank you very much. We will now give the floor to everyone who want to ask questions or who want some explanation. So the floor is open for discussion. Huh? The talk is open for discussion. So if you have any questions, please go ahead.
Thank you very much, Dr. Saleh, for this very nice talk and very nice result on this nanofluid for thermal solar application. I have a question. As you mentioned, the size of nanoparticle is very important to enhance the thermal conductivity. because for small size, the surface area increases and there is a big contact between nanoparticle and the solution. And also for small nanoparticle, the suspension is more stable, I expect. And also, one has to choose material with high thermal conductivity. For this reason, you choose copper.
Exactly.
And you obtain very important, very interesting result with more than 30% of enhancement of thermal conductivity of nanofluid. But my question is, if we consider, for example, graphene or carbon nanotube with 10 times higher thermal conductivity than copper, is it possible, with decreasing the size of this nanoparticle, keeping nanoparticle with small size, to have higher enhancement for thermal conductivity of nanofluid?
In regard to the carbon nanotubes, Prof, or in regard
or
to
graphene, because as you know, graphene thermal conductivity of graphene is 10 times higher than copper.
Yes.
And
Yes,
for
Prof.
that reason, maybe if we consider nanoparticle of graphene or carbon nanotube, we can have higher thermal conductivity of this material and then increase the thermal conductivity of the nano fluid.
Yes, Prof. Actually, there are scientists who prove it that carbon nanotubes and graphene could have higher thermal conductivity enhancement compared to even metallic nanoparticles. It was even published in many reviews and so on. For the simple reason, as you mentioned it, Prof, these carbon-based nanomaterials, they have higher thermal conductivity compared to these metallic nanoparticles. So by selecting a material which have the higher thermal conductivity, it will lead automatically to higher enhancement. So now the issue of carbon nanotubes and graphene is the way to make them. The cost, Prof. So sometimes you need to use some very sophisticated techniques in order to come up with this. So the problem is the cost only. So we tried previously to use graphene by lasers, but it was very, very hard task for us. We couldn't really come up with the single layer graphene. So the laser ablation, it allowed us to come up with few layers graphene. And of course, few layer graphenes, they will not have high thermal conductivity compared to a single layer. So the issue is the cost, Prof. I believe if the cost will be reduced to produce particularly carbon nanotubes, it will be much better. So why? Because carbon nanotubes, once they absorb the energy, they have higher vibration and they have what we call a one-dimensional structure. They create a network within the nanofluid and they start to interact between each other, which means the heat transfer it become much better in that fashion compared to spherical nanoparticles. I wish in the future we can come up with a strategy which can allow us to create these carbon nanotubes so they can be applied, of course, Prof, in this regard.
Thank you very much. I have another question for PLD, pulsed laser deposition. Are there big difference between what has been done for deposition of 2D materials in vacuum and what you have made with liquid? Oh. You have to.
Because I think is the reason. Yeah. Sorry. Yes, Prof.
So if I understand, you are comparing the hydrothermal and the laser ablation, Professor Youssef?
No, not hydrothermal, because Professor Saleh used. You hear me, Professor Dr. Saleh?
I can't hear. I can't hear. I can't.
Yeah, maybe there is a connection problem.
Okay.
Of I think the network again.
Yeah.
Okay.
You can hear now? Dr. Saleh, you can hear now? No, not yet.
Yes, I can hear, but
Okay.
now I can hear, but I couldn't hear. I couldn't hear before. Yes, please.
My question is pulsed laser technique is used for vacuum, and you used it for liquid.
Yes.
Are there some special difficulty to do that? It is not easy to make plasma in some liquid.
Yeah, Prof. This is actually it's a fantastic process, Prof. The first time I used this technique, I was puzzled to see a plasma happening within the liquid.
Yeah.
And I was puzzled to understand that the liquid could be evaporated around the plasma. Is a very elegant process, but it as I showed you the video, I'm not sure if you follow with the video I showed you.
Yeah, I saw it.
Yeah, it works perfectly, Prof. You can use any material from the periodic table. You can use to create nanoparticles. Even I was thinking recently that we can even use materials, resources from different parts of Africa. Like in Morocco, they have mineral resources. You can convert like different materials to be used in energy storage by using this kind of technique.
Yeah.
You see, you can use any kind of materials, Prof, to do ablation inside the liquids. And why the liquids? Why it's much better? Because imagine with me now, you do this ablation in air. So it's gonna be very difficult. So they use vacuum sometimes, but in vacuum you can create only 10 films.
Yeah.
You can't create nanoparticles. So the liquid, it helps in confining the process. So the particles, they could be created within the cavitation bubble. So that is the beauty of the technique. And I wish that this technique could be implemented
I think
somehow.
If you allowed me, I think there is the key parameter are the ablation rate and the transition from thermal ablation to phase explosion, is it?
Exactly, Prof. Exactly.
Yeah.
Exactly, because it's very fast. You are dealing with the picosecond hair regime, which is a nanosecond, and it's really, really very fantastic technique.
Yeah.
Thank you very much, Dr. Saleh, for this very nice talk and very important and nice result. Thank you very much.
I'm very honored, Prof, to give my talk today to eminent professors. I'm really very honored, Prof, today.
Thank you very much. Thank you very much.
Thank you, Prof.
So is there any other questions? Otherwise, you can just put it in the chat if you don't want to ask now, and we can answer later. Just one question from me, but I put it in the chat, but you answered during the talk, and you show when you compare the hydrothermal and the laser ablation that there is one spot where it's from the when you increase for the what we call the scale up, that the price will decrease very much. So, but the other part of the questions is, you know that the CSP is gigawatt, and a lot of we need a lot of liquid, I guess, for the
Yes.
and therefore, do you think that the scale up will follow that the technology of CSP to go to gigawatt, etc.? Because for molten salt, it's very easy to understand. You can have as much as you want. But if you use these nanoparticles, do you think you can continue to scale up in a very high level? That's
Yes,
one. Yeah.
Why can't we make highly concentrated nanofluids and we dilute them to create hundreds of liters at the end of the day?
Oh.
This is one solution. You can create highly concentrated.
And then you dilute it, yeah.
You dilute.
Yes.
This is one. Second, you can use big lasers. Like here at CSIR, there is a center here in South Africa. They have a very, very big laser. They have metallic sheets on the wall, very big metallic sheets. And they start to scan this metallic sheet, and the base fluid is coming on the top.
Yes.
To take the nanoparticles down. Yeah. It's they flow the water from the top. But I don't support that way because it needs big space and a lot of things. But we can create a space where we can make highly concentrated nanofluids and we can dilute them. That's the best strategy to do.
Yes. The other question is when you talk about the theory, you show, in my opinion, that the theory one can explain the quantum confinement is very important in this process. But I guess the quantum confinement is related to the surface. So I think you use a laser ablation and you make the material out of this copper or whatever, and then you have to control the size by the time of laser or whatever, and then until you get monodispersed nanoparticle. But the quantum confinement is related to the surface, not to the bulk, is it? Or if I understand.
Exactly, Prof. Dealing here, we are trying to deal with the nanoparticles below 10 nanometer here.
Yeah.
So, of course, the quantum confinement is there. If we are speaking about this range.
Yeah. Because this is new. You know that there are not many papers or the technique or the experimental result talking about this area. It's just starting. I saw some theses from United States where they start to study this phenomena of quantum confinement by laser ablation. And this is very interesting. It's a very interesting topic, not only for CSP, but for many applications. You have shown one sketch where there are a lot of applications. So I think your talk is I love it very much because it's a source of inspiration for students to do some new research, some new innovation. Thank you very much.
Thank you, Prof. Thank you very much. It's a great pleasure for me, Prof. Really to be here today and to be a member of the VLU. I am learning, Prof. I'm learning from, as I mentioned, from eminent professors like Professor Abdullah Ben Yusuf. When I'm reading his work, I'm inspired. I want to do a lot in terms of calculations to understand these phenomena. So the VLU is opening the door for us to learn and to understand and to contribute. And we wish to continue with that and to implement these technologies in Morocco and South Africa and Africa in general.
Thank you very much. And by the way, if any of your students or your colleagues in in Africa, in South Africa, want to give talks in the within VLU, they are welcome. They have just to contact us or to contact you, and you contact us, and then we can organize talks. And after the talk, they will get a certificate and etc. etc. I think there is one hand from Yunus Kadar. Yunus Kadar, please go ahead.
Okay, can you hear me?
Yes.
Thank you, Professor Saleh, for this nice presentation. I have one question about how to choose the times type in the molecular dynamic. In the LAMP software.
Sorry, come again. I didn't hear you very well.
How to choose the times type in the molecular dynamics?
This is
because in LAMP software, the default, for example, times type is fixed at 0.01 picosecond.
No, you can change it, of course. Maybe you can contact me, I'll show you how to change it. But selecting the time steps, it's not an easy task. So first you have to understand the velocity or how your molecules, how fast they vibrate in general. So there are, sometimes I go through the literature review and I study, for example, for the case of ethylene glycol. I try my best to understand the molecules of ethylene glycol, their behavior and so on. And from there, I try to select the most suitable time step for that particular molecule. Because remember, ethylene glycol, it has some kind of viscosity compared to water. And the viscosity will have some kind of impact on selecting the time step compared to water. So which means I have to understand the molecule of water. And if I'm using ethylene glycol, I have to understand the molecule of ethylene glycol. So this will allow me to select the best time step in general. And you are more than welcome to write to me, and I can communicate more about this with you, Yunus.
Thank you. Okay, thank you very much.
So is there any questions or requests, or you can also, as I told you, you can write in the chat and we will look afterward and send you the answer. Otherwise, if there is no questions, I would like to thank again our colleague, Dr. Saleh from South Africa, and for this very excellent and interesting talk, where there are a lot of information in science and technology, and we hope that we will see him again, because his talk is really very amazing. And thank you very much. I will communicate with you the next talk. I don't have it in mind, unfortunately, now, but I will send it to you tomorrow morning. So thank you very much. Thank you to Ustad Salem Omar for giving us this opportunity through the Sabaik to have a Zoom, and he's with us the whole time. And thank for everyone for listening and for watching this talk. Thank you.
Thank you very much, Professor. Thank you.
See you soon.
Thank you very much.